Howdy folks, today we're going to go ahead and talk through some information when it comes to bioenergetics. This is chapter 2. So first thing we have is substrates. That's what we're going to use to make whatever energy source we're going to be utilizing for that exercise. So everything is being broken down into the basic energy carrier in the cell, which is known as ATP, adenosine triphosphate. And we're going to be using our major macronutrients, carbohydrates, fats, and proteins. Alcohol is considered a macronutrient for some folks. You obviously don't need it to live, and it metabolizes a lot like fat, in case anybody has any questions there. Bioenergetics is the process that we have inside of our body going all the time of how we're converting these substrates into energy. And this occurs inside of our cell in the cytoplasm or sarcoplasm, we're talking about muscle, and then also inside of the mitochondria. Mitochondria is where that aerobic metabolism is going to occur. Now, metabolism itself is going to be all of the chemical reactions, both catabolism breaking things down and anabolism building things up that's occurring inside of the body. Now, whenever we're looking at the energy that we're utilizing, we're going to be doing this in what's known as calories. A calorie is simply the amount of energy required to increase 1 gram of water 1 degree Celsius from 14.5 to 15.5 Celsius. Now, when we look at calories for humans, we're talking about kilocalories, big C calories, and that's 1,000 little c calories. So it's the amount of energy that's required to take 1 kilogram or 1 liter of water 1 degree Celsius. Hence, when you're exercising, you get warmer because you're literally burning more calories and you're releasing more heat, since not all the energy we're producing is going to be actually 100% used for work. In fact, most of it's actually lost to heat. Now, carbs, fats, proteins are made up of different arrangements of effectively carbon, hydrogen, oxygen, nitrogen, and sulfide in the case of protein. Now, we're going to be breaking those bonds in order to release energy. And the more of those bonds we break, the more energy we're going to get. Now, at rest, most of us are going to be using about 50-50 carbs and fats for energy. Whatever you've eaten most recently is actually going to have you shifting more towards that fuel. And if you hadn't eaten for a long period of time, you're going to be starting to be utilizing more fats as a fuel. Now, we utilize carbohydrates for shorter, high-intensity exercise. The longer duration the exercise, the lower the intensity, the more we're going to be relying on fats for fuels. And so what we have on the right is about the amount of each of those, of the major macronutrients we really use for energy, of carbs and fats. Proteins are going to be used a little bit for energy, but not enough that it's really worth thinking or really going into depth about, unless you're talking about some hardcore starvation situations and someone that's actually pretty darn lean in the first place. So if you noticed over there, guys, we have a whole lot more energy stored inside of our body in the form of fat than we do carbohydrate. Fat is the most calorically dense of all of our macronutrients. It's effectively just carbon and hydrogen with a carboxyl, so a carbon and some oxygen at one end. And so it's got a huge amount of energy and it's able to be stored pretty compactly. Whereas carbohydrates, we've got a lot of oxygen involved in there and it's going to require more space and storage. So that's why we don't try to just store just carbs inside of our cells. We're going to top that out, and the storage form for that is what's known as glycogen. And we store that only in our muscle and in our liver. And we're going to be utilizing the glycogen in our muscles to do the exercise. Now, it's only the glycogen stored in that muscle that's being used in exercise that's going to use it. The glycogen stored in our liver can be freed up from our liver and then go throughout the rest of our body. Now, take some time and really make sure you understand this flow chart. This flow chart shows you guys how each of those macronutrients can convert from one into another. Now, if we have too much of any macronutrient, more specifically going to be carbohydrates, that's going to convert to fat. Too much fat is going to stay as fat. It's going to be stored as fat. If we're not taking enough calories, doesn't matter if it's all fat that we're taking in, all protein, or all carbohydrate, we're going to be running at a deficit. So we're going to be removing fat from our fat storage. We're going to be removing or depleting our glycogen stores. And we're going to be utilizing, obviously, whatever nutrients you have in your body for as much energy that you need in order to keep going. So make sure you understand how all of those are going to work together. Now, we're going to only break down as much energy as is necessary to keep up the demands of the exercise we're doing. The body is all about efficiency, and if it can help it, it wants to make sure that it's never burning any more calories than it needs at any given time. So if we have more substrates available, we're going to be able to run a system faster. If we've got more enzymes that are going to allow it to happen, we're going to get more of that reaction to occur. So what's going to be actually controlling the rate of which we're going to be breaking down any of these nutrients is going to be, they're going to be catalyzed by what's known as enzymes. Enzymes are very specific configurations of proteins that are going to serve effectively a specific role that's going to help take substrate A and remove something with it, or remove something from it, or add something to it, so now it becomes B. And then another enzyme is going to change B into C, and then C into D. Now, this is really useful because it decreases what's known as activation energy. Activation energy is the energy required to make something happen. So, for example, I have a bunch of sheets of paper around me at any given time. This paper is not just going to burst into flame. It needs enough activation energy in order to go, or energy applied to it in order to cause it to just start to burn. So if I obviously applied a flame to it, the paper would light on fire and it would burn. Now, if I tried the same thing with a really big log, well, I could put a lighter next to it for a second, but it's not going to light on fire because it requires more activation energy than a single sheet of paper. That's where you're going to have smaller pieces of wood that will eventually build up into the bigger piece of wood that's going to allow it to burn. So when we're looking at this, we're seeing that these enzymes are going to allow for these cascades of reactions to occur. Now, the first one at the beginning that effectively serves as the gatekeeper is what's known as the rate-limiting enzyme. This is the doorman. It makes sure that things don't just run out of control, and it's going to slow things down by what's known as negative feedback. So what that means is once we have a lot of the products at the end of that enzymatic cascade, those products are going to inhibit that initial enzyme so that we're not producing any more than we need. Because once again, we don't want this runaway turnover. Positive feedback is once you get the end product, you then create even more of that product and keep going and speeding up the cycle, which is fine when it comes to learning skills, but is horrible when it comes to homeostasis. The body is all about negative feedback. Once we get the levels to the level we want, we're not going to keep producing more until our levels go down. And then, because we don't have as much negative feedback, we're going to turn that production back up to get back up to those levels we wanted. Now, we talked about ATP a little bit at the beginning. There she is, which is going to be an adenine, which is one of our nucleotide bases with a ribose attached to it. And then in ATP, it's triphosphate. So we're going to have 3 phosphates that are going to be bound together. When we go ahead and cleave one of them off, we're going to create, or we're going to break one of those diphosphate bonds, and that's going to release energy, which that energy is going to allow us to have those enzymatic reactions occur. So it's important to understand that we only have a finite amount of ATP in each of our cells, and we're turning it over all the time. So we have to do something in order to go ahead and replenish it. And we're going to do this through 3 basic systems, but effectively the oxidative breaks into 2 individuals. Our first is what's known as our ATP-PCr system. This is going to be just ATP and phosphocreatine, and one enzyme known as creatine kinase that's going to remove a phosphate from phosphocreatine and attach it to an ADP to replenish it back into ATP, adenosine diphosphate, into adenosine triphosphate. We then have our anaerobic glycolytic system, and this is where we're going to break down glucose into its final product, which is going to be lactate and a proton. The proton is hydrogen. Hydrogen, when it accumulates, decreases pH, makes cells more acidic, makes the blood more acidic, which in turn is going to decrease performance, and it's what causes the burn. This is an anaerobic energy system. Doesn't need oxygen, lasts for up to about 2 minutes, and it sucks, and it's really uncomfortable to use. Then we have our oxidative system, which is going to come in 2 major branches. One, we have our aerobic glycolytic system, which is going to be breaking down glucose into pyruvate, which gets converted into acetyl-CoA. Acetyl-CoA goes through the citric acid cycle. Those products and the products of glycolysis of NADH and FADH2 then go into the electron transport chain, and that's when we have our final production of ATP at the end of that system. Now, we then have our beta oxidative system. So that's going to be beta oxidation is where we're going to break down fats into NADH, FADH2, and acetyl-CoA. That acetyl-CoA is also going to go into the citric acid cycle. In the mitochondria is where all the beta oxidation occurs, along with the citric acid cycle and the electron transport chain. Glycolysis in the ATP-PCr system occurs in the sarcoplasm. So those products, once again, are going to go through that system aerobically, and that's going to go ahead and produce energy for what the body is trying to do. So ATP, the shortest of our energy system, lasts on average for about 6 seconds. Anywhere from 3 to 15 would be the range. This is the highest intensity. This is throwing the shot put, sprinting a 40-yard dash. It gets depleted rapidly. But however, this is the point where you're doing hard work, but it doesn't feel hard. It's like, yeah, I'm giving myself maximal effort, but I'm not really breathing hard. I'm not really feeling the burn. I'm just working my way through it. Now, creatine kinase is going to be the enzyme that's going to catalyze this. It's obviously going to be active whenever we have a greater amount of ADP and a lower amount of ATP. And the opposite is true. We then have anaerobic glycolysis. This is going to last from about 15 seconds to 2 minutes. And this is going to be still moderate to high intensity. So think running something like a 400 meter or an 800 meter that's just really brutal and hard to do, or playing like full court press basketball at a high pace rate where it's really, you're giving high efforts, not maximal, but pretty high efforts, and you can only do it for a limited period of time. And this is using glucose via glycolysis. You can see how we're going to go ahead and use a little bit of ATP for activation energy from glucose, glycogen that's actually already happened, so you don't have to use the activation energy when it comes to breaking that down for energy. And we're only going to net effectively a total of 2 ATP if we go from glucose, 3 if we're going from glycogen. So it doesn't give us a lot of energy. The phosphocreatine ATP system only nets us 1. We don't really get into bigger production, so we get into aerobic metabolism. Now, this is, once again, not really productive in producing a lot of energy. It's going to give us some byproducts that get to be pretty uncomfortable, but it's something that you can do without oxygen. So it's something we can use to support that really high intensity exercise where otherwise we wouldn't be able to do that aerobically. And so in the glycolytic system, the major rate limiting enzyme is what's known as phosphofructokinase, also known as PFK. It's the 3rd step in the system, and it turns out when we've got a low amount of ATP, high amount of ADP, it's going to be active, and the opposite is going to be true. Now, once we go over 2 minutes of exercise, now we're starting to get really into aerobic glycolysis. So we're going to break down glucose through glycolysis, which we get that pyruvate. That pyruvate will convert into acetyl-CoA. Acetyl-CoA goes through the Krebs cycle, also known as the citric acid cycle. And then that is going to feed into the electron transport chain through all those protons that we get from NADH, and then finally help regenerate or generate the ATP. And notice, guys, where we only net 2 from just plain glycolysis, when we go all the way through this entire system, now we're talking about getting over 30 ATP. So this right here is the citric acid cycle of showing the many steps. I'm never going to make you guys memorize this, but understanding this is occurring in the mitochondria and is incredibly important for energy production. Now, when we're talking about breaking down glucose, we're talking about net total of 32 ATP. Now, we lost 2 for activation, so we technically created 34, but we net 32. Now, if we go from glycogen, we get a net of 33 ATP. So that gives us even more energy than what we would have done before, because we only had to use 1 for activation. And then you can also see how we're going to get those protons to create the electrochemical gradient in the electron transport chain in the bottom right, and that's going to allow us for that energy production. And then how much ATP we net from every NADH and every FADH too. Now, when it comes to breakdown of fats, we are going to get a crazy amount of energy because we're going to be netting NADH and FADH2 through all of those systems, which then is going to go ahead and feed into the citric acid cycle through the acetyl-CoA. We're cleaving off 2 carbons of a time for the fatty acids, and all of those will then feed in eventually to the electron transport chain. Now, protein, like I said, we're not really relying on energy for energy pretty much ever, so don't really worry about it. Well, we can talk about it at length if you guys are interested, but for the most part, it's nothing that's going to really come up enough that's worth really getting too into the weeds with, much less really being concerned about. Now, same type of situation as we had with PFK, we're going to have negative feedback through an enzyme known as isocitrate dehydrogenase. And that is going to be inhibited when we have high amounts of ATP, because why go through more metabolism if you got plenty of energy available? But when we have a lot of ADP, then we're going to start to see this becoming activated. And understanding this figure is really important, guys, because it's going to show you guys how we have the interplay of all of these different energy systems, how we're going to be obviously breaking down carbs, breaking down fats, delivering oxygen, what parts of the cell is going to be utilizing oxygen, where this is going to be occurring in different parts of the cell, along with how we're going to be storing that glycogen inside of our muscles, fat inside of our fat cells. Not that we don't have fats naturally stored inside of our muscles along with glycogen, naturally stored inside of our muscles. And we're going to find that once we produce that lactate, it can be broken down by our type 1 slow twitch muscle fibers. It can also be broken down and regenerated in glucose in our liver, but it can also be utilized as fuel by both our brain and our heart. Lactate is not a waste product, it's a fuel source. It's that protein that that proton that comes with it that drops the pH. That's where the issue is. So we see an inverse relationship between how quickly we can provide energy by an energy system and its capacity to produce energy. So we get the energy really rapidly from the ATP-PCr system, but it bonks out super quick. And the opposite is true when it comes to fatty acid metabolism. So take your time, read through this slide, and then, looking at the tables and then understanding these graphs. Now, what we're going to find is obviously individual muscle fibers are going to have preferential fuel sources, and we can always improve our energy systems by increasing the amount of mitochondria in our cells, increasing the amount of our enzymes related to those energy systems in our cells, and increasing the storage of those nutrients inside of our cells. That's something that takes time, but it's a specific adaptation to the imposed demands that you're going through with your training. So, yes, your type 1 fibers typically are better at oxidative work. Your type 2As are much better anaerobic glycolytic, and your type 2Xs are naturally much better at ATP-PCr. But through training, we can see enhancements, and those fibers start to take on characteristics of the fiber type that you're tapping into the most for your training. And so what we're going to find is different enzymes are going to be obviously incredibly important for energy production, but we're going to see that certain enzymes don't break down constituents as fast as others. So that's why seeing what's known as your SDH, succinate dehydrogenase levels, and your CS, citrate synthase levels, are going to be indicative of actually aerobic performance. Those are both important in the Krebs cycle, or the citric acid cycle, and that's going to allow for the much more rapid aerobic metabolism of both fats and carbohydrates. And we're going to find that individuals that are highly trained, they're naturally going to have these enzymes that are much more productive. And you're increasing enzyme activity by increasing enzyme number for the most part. You can't really make an enzyme more efficient. It's the equivalent of having a factory. Each factory can only produce something at a certain speed. But if we build more factories, we can now create more of the same product within the same period of time. So, type 1s, aerobic. Type 2, anaerobic. Training is going to make them take on the characteristics of the other ones like we talked about. And we're going to find that we're also going to be uptaking more oxygen. We're going to be causing enhancements, or not enhancements, but acute increases in output through our heart, through our respiratory system that we'll get into at a later date, and how those in turn are going to feed more oxygen to the muscles. So we're going to be able to maintain that exercise output for a longer period of time. So when it comes to looking at energy system, guys, my advice to you is think of it like a triangle. The base of everything is aerobic beta oxidation, so breaking down fats. That's the background that's happening if you guys are just sitting there listening to this lecture. Now, as we start to increase our intensity, that's where we're going to see more aerobic glycolysis. And then we're eventually going to go over that aerobic threshold, and now we're in anaerobic glycolysis, and the very top of it is going to be the ATP-PCr. Now, what regenerates the ATP-PCr system is our aerobic systems. What regenerates our anaerobic glycolysis system is our aerobic systems. So we need to have a good aerobic base for pretty much everything so that we're going to be able to recover from a bout of exercise and perform again. Now, each athlete, the way their triangle is going to be shaped, which part of the triangle is going to be the most emphasized, is going to come down to specificity. But understanding that we need to have the bigger foundation, so we're going to have the higher performance with any endeavor we're going to have our athletes be working on. So thanks for listening, guys. If you have questions, comments, concerns, go ahead and drop that under here or shoot me an email, and I'll be more than happy to elaborate on anything. Have a great day.